You know, we've seen the use of the def keyword, DEF. And maybe we wrote a function that took two numbers and then returned their sum, like this. Z is equal to x plus y, return z. That's a function. Then when you're ready to call it, you could do a is equal to add 1 comma 2. Now that's a really simple function. You wouldn't probably write it that way. But there it is. That's a function. But you can write a function that calls itself. However, it has to be very carefully structured, or else it runs forever. So do go ahead and type this in. Let's call this function B-Day for birthday. So it's going to print happy birthday, and then it's going to call itself again. Why? That way it'll print happy birthday more than once. Now this is bad recursion. This is not correctly written. It's going to give us an error. When we run it, it's going to call itself too many times. It's going to run out of memory and break. Sorry. Here we go. So go ahead and run that, and you'll see that it does print birthday over and over, or it doesn't. What did I do wrong? I didn't even call the function. If you just have a def, but you don't have anything that's unindented besides the def, your program doesn't do anything. Okay, there we do. There we go. Yay! It does that a lot. Eventually it runs out of memory. You know, the operating system only gives this program so much memory, and eventually we ran it out. Why? Because each time the program calls a function, it has to allocate a little bit more memory. And each time it leaves that function, it releases that memory. But in this case, that memory never gets released. So it's like you, I'm not going to even give a simile. There's no real world comparisons. So that's bad recursion. I'm going to put a comment here. Call this bad recursion. Runs out of memory. So I'm going to comment this call out since it's bad. Now let's define a good recursive routine that'll only print it a certain number of times. What are we going to call this one? We're going to call this one HB Day for happy birthday. We're happier because it's actually going to run. But we're going to pass a variable in that specifies how many times it runs. But we need to provide it a way to get out. If x is less than or equal to 0, return. Don't call yourself anymore. Otherwise, x minus equals 1, subtract 1 from x, and then call yourself again. I forgot to actually print anything. Above that x minus equals 1, let's stick the word print. Happy birthday. And heck, let's print out x too, just so that we can watch that number. So now we're going to do HB Day, but we're going to, I want to print happy birthday 5 times. So I put 5 in there. Oh, I made a mistake on this line. Right here. Why? What is wrong with this line? Anybody spot it? I have to pass in an argument. I have to have this parameter be filled. So we're going to pass in x. And as a matter of fact, I apologize for this, but I want to rewrite these completely. I'm going to comment those two lines out because I'm rewriting them completely. I'm just going to put HB day x minus 1. That shortens it to one line of code rather than two. It would have worked as I had just done it, but this will be a little bit cleaner. All right, I think I figured out a real-world simile that I'm almost comfortable with saying. Say that each time your program calls a function, it goes into a room. And each time it returns from the room. Recursion is like if you go into a room and then there's another door and you walk into that room, but that room is actually a copy of this room. And then you call yourself again, so you walk into another room. But finally, you need to start hitting some returns so that you can walk all the way out, get out of all the doors. So that's what this is doing. We're going to go into this room carrying a 5. All right, now we're inside HB day, and x is equal to 5. Is x less than 0? No, it's 5. So we print happy birthday, 5. Then, with the value of x minus 1, well, x was 5, it's going to become 4 when we pass it back in. We go into the next room, carrying a 4. So it loops back up here. Is x less, no, loop is not the right word. There's no looping involved. Instead, we're calling ourselves. Is x less than 0? Well, no, it's still 4. So we print happy birthday 4. And then we call ourselves again with another smaller value. We take 1 from x, pass that in as an argument, so we're entering our next room. X is equal to what? It was 4, now it's 3. Yeah, you can see where this is going. X is less than 0? Nope. Print happy birthday, call ourselves again with x is equal to 2. Is x less than 0? Nope. Print happy birthday, call ourselves with a 1. Is x less than 0? No, it's 1. Print happy birthday, call ourselves again. So now we're 5 rooms deep into our house. And then in the next room, we go in there carrying a 0. Is x less than or equal to 0? No, no longer is it true. So we return. And here's where it gets kind of strange. When it returns from here, it returns there, it returns there, it returns there, and we're done. That looks weird, but there's no other code after this HB day. This is our last thing in that function. So all we need to do is return at some point, and then that's going to get us all the way out of the code, out of that function. So once we hit this, there are 2 parts of a recursive function. One is called the default, and the other is called the recursive. This is the default. This is when you finally reach the end of your recursion, and you're going to start going back out. So your recursive functions will have some kind of if statement to differentiate between the default state, which is when you want it to stop calling itself, and the recursion call. So that's the way recursion works. Is there an easier way to print happy birthday 5 times in a row? Yeah, of course there is. We could just use a loop, you know. It'd be way easier to write. It would be instantly obvious in your brain, since you know what looping is. We've seen it a couple times. But there are things you can do with recursion that are very difficult to do with a more linear looping kind of programming. linear meaning not calling itself with it. However, those things are so complicated pretty much that we're not going to demonstrate those. But like advanced sorting algorithms or processing of a lot of data, it's useful if you can split the tasks up into smaller pieces, especially if you're running on something with multiple processors, so that you can get multiple pieces of it going at the same time. But anyways, we're going to write one more recursive function. This recursive function is going to add all the numbers. You know, it's going to do something called summation. If you do the summation of 10, it'll add 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. So let's write a function called summation. And it's going to take a parameter that we call n, so that we can say I want to know the summation of 3, and it'll add 3 plus 2 plus 1 and return this. We need a recursive case. If n, if n is less than or equal to 0, just return a 0. We're not gonna be adding anything past that point. Else return n plus, and here's our recursion case, summation of n minus 1. So now if I do this, print the summation of 5, it should print 5 plus, well, it's not going to print 5 plus 4 plus 3 plus 2 plus 1, but it's going to add those numbers up, return that, and then print that result. So 5 plus 4 is a 9, plus 3 is a 12, plus 2 is a 14, plus 1 is a 15. This ought to print 15 if I wrote it correctly. Okay, and it did. Now I'm not going to walk through it, walking back across the room, pretending I'm carrying data into different rooms this time. But what is it doing? Return n, well, we passed in a 5, so n is equal to 5, plus the summation of n minus 1, so we're changing it into 4 for our next call, which does a return n plus the summation of 3, which returns n plus the summation of 2, which returns n plus the summation of 1, which returns n plus the summation of 0. Now n is equal to 0. It returns a 0. The next one returns a 1. The next one returns a 3. 1 plus 2 is 3. The next one returns a 6. Because 3 plus 3 is 6. The next one, now it's a 6. N was equal to 4, so it returns a 10. And then n was 5, returning a 5. I don't know if there's a clearer way for me to explain that unless I just draw it out on the board. So we're going to say that we're going in summation with a value of 5. And down here we're going to, so we call ourselves with a summation of 4. We call ourselves with a summation of 3. Call ourselves with a summation of 2. Why didn't I just pick 3? Summation of 1. And then the summation of 0, which returns a 0. So 0, now we've got 0. We return that back. Now we have a 1. 0 to plus 1, we return a 1. A 1 plus a 2 is a 3. A 3 plus a 3 is a 6, because now we're doing our returns. A 6 plus a 4 is a 10. And then our last one, our last return, is a 10 plus a 5 is 15. If that doesn't make sense, that's all right. You know, you're going to have more chances to learn this stuff in other classes. But that's the idea behind recursion. When a function calls itself. When you write a recursive function, you have to make sure that there's a way for it to stop calling itself. Otherwise, it does that thing where it calls itself infinitely until it runs out of memory. All right. I'm going to do a quick Google asking if there are any other examples of recursion. That's worth talking about. Oh yeah, let's do a tree. Let's draw a tree using recursion. So let's write a new piece of code. File new, do a save as and call it tree. The way we're going to draw the tree is we're going to write a function called branch. And when we call branch, what it's going to do is it's going to turn left, go forward a little bit, and then say that was the end. Then it's going to back up, turn a little bit to the right, go forward that amount, come back, and it's going to turn to the left again a little bit, go forward, and then call itself again. So you can see what it's going to do. Left, right, middle. But with smaller numbers each time so that it doesn't just branch infinitely. So let's, we have to import our turtle. Import turtle. T is equal to turtle dot capital turtle, parentheses in parentheses. So we're going to define a branch function, where n is the length of this particular stem of the branch. So we have to have our default case so that if n gets too small, we back out. So let's just say if n is less than 20 pixels, if that doesn't look good, we'll fix it. If n is less than 20 pixels, return. All right, now let's turn to the left a certain number of degrees, like maybe 30. T dot left, 30. And then call branch, but with a smaller value. N minus 10, n divided by 2, something that'll decrease its value. Since we turned 30 degrees, we need to turn right another 30 and then another 30, so I'm going to do a t dot right 60. Then I'm going to call branch again with n minus 2. So our recursive function is actually calling itself 3 times per iteration. Because we're going to call ourselves, I am making a mistake here. I'm going to have to look at my notes. I'm going to turn left. See, I went left 30 degrees, then I went right 60 degrees, and now I want to go back up to where I was. So t dot left 30 degrees again. That sets us back, on the straight and narrow where we were. And then branch n divided by 2. All right, forgive me, I have to peek at my notes because I've made a mistake there. Okay, there it is. Once we're done with drawing our branch, we want to go back the same number of pixels that we went forward. I forgot to draw anything. Okay, so I'm going to have to add a draw statement. before all this stuff and then after all this stuff. So I'm making an insertion here. T dot forward, let's go forward in pixels. So that's new. So I'm putting a comment there to say that that's new. And then we want to back up the same number of pixels. So at the bottom, T dot back in pixels. So add that too. That ought to do it. Let's call branch with a link like the 100. Let's see if I have any syntax errors. Alright, we could probably make that cooler. What if instead of n divided by 2 we did n minus 20? So I'm going to change all those n divided by 2's to n minus 20. Dividing it by 2 made it too short. And this is a good example of a recursive thing that would be very difficult to do with a loop. I don't know how you would draw this tree with a loop. Yeah. What would make that cooler? Well, what if we went straight up? The problem is that the turtle starts going off to the right because in turtle land that's 0 degrees, whereas north is 0 degrees in our numbering system. So we could make ourselves go north before we started going. So why don't we just do T dot left 90 degrees so that we're going north? I'm still not totally thrilled with the way that it looks. And why don't we set our speed fast to the maximal speed? T dot speed parentheses 0. So I added 2 statements in front of our call to branch. Those 2. All right, that's a little better. I'm going to check to see the values that I used on the last demonstration. Okay, I turned 20 degrees rather than 30. So you see our 30s, changed those to 20. And our 60, changed that to 40. We should make these variables so that they're very easy to fix. So I made a change to that one. I made it 20. I made a change to that one. I made it 40. And I made a change to that one. Made that one 20. I kind of like that. Why don't we make it kind of a circular tree? Let's turn left again 90 degrees, and then draw another branch, and then turn left 90 degrees, draw another branch, and then turn left one more time, and draw another branch. So I'm going to add 3 statements down here to the bottom. Then I'm going to wander around and make sure everybody's got this going. So down here, after our call to branch, T dot left 90. And let's just do 3 branches. So let T dot left 120. Nope. Yeah, this should work. That's new. And then call branch again with the same length of 100. And then let's call t dot left 120 one more time. And then branch 100 one more time. So all of this stuff is new. Probably would have looked better at 90 degrees rather than 120. Whatever.
That actually looks better than 90.
Okay.
Because there's straight lines and boxy in the middle.
Okay. Alrighty. So that's using recursion to draw a tree. You can also use recursion to draw a spiral. Let's make that the very, very last thing we do. But is anybody having typos on this? Wave your hand now. Jump up, throw a book at me. Okay, so we're going to do a spiral. Define spiral with n. If n is less than 20, return. That's our default case. We've got to be able to escape. Got to start backing out of our rooms. So let's go forward in t dot forward in pixels. Then let's turn left, just a small distance, maybe 10 degrees. And then let's call spiral with n minus 10. With n times point. Yeah, let's just do n minus 10. We can always play with those values later. Now we need to back up, same distance we went forward. So t dot back, n pixels. That'll do it. Now we need to call spiral. Unfortunately, it's going to print our spiral right on top of our tree. And this is taking a long time to draw every time. We could comment that code out, the tree. It was a little bit too big. Well, let's change spiral from 100 to 50. And then let's comment out our tree, just for now. I'm going to take all 7 of these statements, highlight them, do format indent region. That comments out all 7 of those lines at one time. No, it doesn't. Undo that. Control Z. Highlight them all. And don't choose indent. That's kind of dumb. Instead, just do comment out region. Or just add them by hand. That way it won't draw the tree before it does the spiral. Okay, that was singularly uninteresting. Maybe instead of left 10, let's do that like left 45 degrees. Well, this is just looking all lousy. I'm going to comment out the back statement. I don't want that there anymore because we're not drawing a tree, we're just going forward. instead of n minus 10, let's change that to n times 0.9, it's meaning 90% of its former value. And we're kind of getting there. And let's make this say if n is less than 5, right there. So I've changed that line. I've changed that line. I'm just tweaking it to get it to draw a spiral. There we go. Good enough. And I don't know what I did wrong so that it wasn't able to back out. But whatever. Okay. So we used recursion. Drawing a spiral with a loop would not have been that hard. But drawing that tree with a loop would have really been hard. Recursion is by far the best way to do the tree. So, thinking that the spiral isn't as cool as the tree, I'm going to just, I don't know, delete it, maybe comment it out. All we have to do is comment out the call to spiral. So I'm just going to put a star and a hashtag in front of this. Then I'm going to uncomment out my tree because I liked that code. That was way more impressive. And that'll be enough. We can call it a day. Yeah. Okay, I'm going to scroll back up to the tree. If you didn't get the spiral done, that's okay. Wasn't that cool anyways? Anybody have trouble getting the tree to work? Anybody have trouble getting the spiral to work? And you do want to finish it.
Instead of 9 times. So 99% number. Yeah. Should show that. I should be some water. What's that called?
Well, that's cool. What values did you use for that? So cool. All right, y'all want to see something cool? Change 20 and 40 and 20 to 300, 600, 300. It makes a cool shape. Instead of 20, 40, 20, make it 300, 600, 300. It's not really a tree anymore. It's a snowflake. It's so cool. Good job on that. Neato keen. If we could speed it up even further, I'd like to make it draw, distances longer than 20 so that it got, almost infinitely small. I think I'll do that, but I'm going to just leave this running on the side while I Google up what may be the most famous example of recursion, the Mandelbrot. Fractal. I bet a lot of y'all have seen that. This is done with recursion. And what's kind of cool about it is that the mathematical function that derives it, you can zoom in endlessly on it. It is endlessly complex. There is no point where you can zoom in on this formula if implemented correctly. don't want to watch 16 minutes of Zoom. Can we have one that's short? Anyways, you see what I mean. It's a function solved by recursion that generates an infinite amount of detail. And fractals are useful for more than just drawing weird pictures like this. We'll talk about fractals. You can get a program. Alrighty, we'll call it a day. There's a drop box. In the wrong place. That was the right place. If you don't see it down in the in-class stuff, you can scroll back and find it up at the very top. There's a no category. Your flowchart has a grade, but that grade is not going to show up when you use this. Total grade. That actually in your exam. That question that says I have done the flowchart or I'm doing the flowchart is for 20 points.